Hey, welcome to the Explainer. Today, we're diving into one of the most important, but honestly, most misunderstood principles in software design, the Liskov Substitution Principle. Yep, it's the L in solid. And trust me, getting this one right, that's the secret to making inheritance actually work for you, not against you.
All right, let me ask you something. Out of all those solid principles, which one do you think really trips people up the most? You know, the one that leads to those super tricky, hard-to-find bugs. It seems so simple on the surface, but it's got a lot of depth.
Yep, you got it. It's the Liskov Substitution Principle. And that's exactly what we're digging into today. Because honestly, if you can master LSP, you're on your way to building object-oriented systems that are actually reliable and predictable. It's all about making sure our abstractions, our promises, actually hold up. So let's see what that really means. Okay, so first things first. What in the world is the Liskov Substitution Principle? Let's get that official definition out of the way just so we're all on the same page. So here's the textbook definition. Subclasses must be substitutable for their base classes without altering the correctness of the program. Okay, so what does that actually mean? In plain English, it just means that any child class should be able to slot right into the place of its parent class, and the program shouldn't even blank. No crashes, no weird behavior, nothing. Let's break that down even further. Think of it like this. Step 1. Your code is using some kind of base class, right? The general version. Step 2, you decide to swap it out for a more specific child class. Step 3, if you've done this right, if you followed LSP, the program must keep working perfectly. It shouldn't have a clue that you made a switch. That's the whole point. You know what? To make this crystal clear, let's forget about code for a second. Let's use a really simple analogy. Think about something you might have in your kitchen. This is such a great way to think about it. So if you sell a machine and you call it a fruit juicer, you're making a promise, right? You're telling people, hey, you can put fruit in this. So when I buy it, I expect to be able to toss an apple in there and get apple juice. But what if it only works with oranges? Well, it just broke the promise. It's not really a fruit juicer at all, is it? It's an orange juicer. The problem isn't the machine itself, it's that we've modeled it wrong. We gave it the wrong name, the wrong abstraction, and that is exactly what happens in our code. And that right there brings us to the #1 trap that developers fall into with inheritance. It's this simple little idea that feels so right, but it leads to so many design headaches. So here's the big question, the one you really need to ask. Just because something is a type of something else in the real world, is that enough? Is that all we need to create an inheritance relationship in our code? You know, the classic example, a square is a rectangle. Seems logical, right? So it should inherit. But is that actually correct? And the answer, maybe surprisingly, is a hard no. And this, right here, is the absolute heart of the Liskov Substitution Principle. Inheritance isn't about an is-a relationship. It's about a behaves-like relationship. It's all about behavioral compatibility. The child has to behave in a way that doesn't break the promises made by the parent. Let's use a classic example to really hammer this home. I mean, in real life, a penguin is a bird. Nobody's going to argue with that. But what happens when we try to put that logic into our code? We run straight into a wall, and that wall is behavior. Okay, so here's the problem. If we have a bird class and it has a fly method, we are making a promise. We're saying anything that is a bird can fly. But a penguin can't fly. So what are our options? We can make the fly method for the penguin do nothing, or even worse, make it throw an error. The second we do that, our penguin is no longer a safe substitute for a bird. It breaks the expected behavior. And just like that, you violated LSP. All right, let's take this out of the animal kingdom and into some actual code. We're going to look at a super common example that trips up so many developers, the infamous rectangle and square problem. So first, let's set the ground rules. Let's establish the contract for our base class, the rectangle. A rectangle is simple. It has a width and it has a height, and you can change them independently of each other. Its area is always width times height. That's the deal. It's simple, it's predictable. So let's see this work. We make a new rectangle, we set the width to 5, we set the height to 10, then we ask for the area. What do we get? 50. Perfect. The contract is being honored, everything's working just like it should. Okay, now for the tricky part, the substitution. Now in geometry class, we all learned that a square is a special kind of rectangle, right? So it seems totally logical to make square a child class of rectangle. So let's do it. Let's swap out that rectangle object for a square and run the exact same piece of code.
And what happens? Boom! Our program is now broken. Not a crash, but something way more sinister. We set the width to 5. Great. Then we set the height to 10. But since a square has to have equal sides, setting the height to 10 secretly changed the width to 10 as well. So now, when our program asks for the area, it gets 100. It was expecting 50. The behavior has completely changed. The correctness of the program is gone. This is a textbook LSP violation.
So how can you catch this in your own code before it causes problems? Well, there's one simple question you need to ask. Think of it as the ultimate litmus test for LSP. All right, so we've seen the problem pretty clearly, right? We know what it looks like, so the next logical question is, how do we fix it? How do we actually design our systems so they don't fall into this trap? The main idea, the big fix, is all about separating behaviors. Instead of trying to cram everything into one giant base class, you use more specific, more focused abstractions. So for our birds, maybe you have an iFlyable interface. Not every bird has to implement. And for our shapes, sometimes the simplest solution is the best one. Just admit that a square doesn't behave like a rectangle and keep them as two totally separate classes. The whole goal here is to stop forcing a child class to pretend it has a behavior that it just doesn't. Okay, so we've covered the what and the how, but let's wrap this up with the most important part, the why. Why should you even care about the Liskov substitution principle? Why does this actually matter? It matters because the consequences of getting it wrong are, well, they're pretty bad. When you violate LSP, you're planting these little time bombs in your code, these hidden bugs that are an absolute nightmare to track down later. Your program starts doing things you never expected. You get weird runtime errors that you can't seem to reproduce. And at the end of the day, you end up with APIs and systems that nobody can trust. They're unreliable, and they erode all confidence in your code base. So look, if you walk away from this explainer with only one thing, I want it to be this question. Seriously, burn this into your brain. Every single time you think about using inheritance, you have to ask yourself, if I substitute this child class for its parent anywhere in my entire system, will it all still work perfectly? And if the answer isn't a loud, confident yes, then you need to stop and rethink your design. At the end of the day, it really all boils down to one simple idea. LSP is about a contract. It's a promise. The parent class makes a promise about how it will behave, and any child class that inherits from it has to honor that promise. Period. No exceptions. It's not allowed to weaken that contract. Because in software, just like in real life, when you start breaking promises, things get chaotic really, really fast.